Okay, so let's briefly look at the solution region boundary conditions. Solution region boundary conditions. So if we have a problem region with a boundary on the outside, gamma 1, and then we have an internal boundary, gamma 2, and so then we have two subdomains. We have subdomain 1 and an internal subdomain 2. And so we might be interested in solving the problem within gamma 1. So for example, we could have a problem such as the electrostatic equation in terms of scalar potential, and then we'd need to solve this problem within this region where gamma 1 and gamma 2 are called subdomains. Those are surface regions or volume regions if it's 3D, and gamma 1 and gamma 2 are the boundary conditions where gamma 2 is the internal boundary and gamma 2 is the internal subdomain. So for a practical problem, we may have many internal subdomains and many internal boundaries, but there'll be only one overall outer boundary that encompasses the whole problem, and that may be surrounded by some air region outside of the main problem that we want to look at. So if this was an electrical machine, then this outer boundary could be defining the external part where within it is an air region, which would be defined by omega 1. Okay? So then the other type of solution or problem region is a open problem. And but we're not going to talk about open problems so much. They're more common in wave propagation than power type of problems. But you would have some boundary with some value, and then you might want to know what the field is far out from it. So you would have the field can propagate outwards away from this boundary value, and so you might, this could be your coordinates x and y. You might have some value defined by vector r prime, and then you might say, okay, what is the value at position r, that the magnetic value, for example, and so the value at R would be related to the distance away from the boundary, so R minus R prime. So for example, if you look up the electric scalar potential, you can have boundary problems, integral problems where you want to know, you have some charge value and you want to know what it is at some distance away. Where rho s would be some charge on the surface. So you'd need to solve an integral to evaluate that. So this is an example of an external subdomain solution. It would be on it's on an open region going to infinity. So you know that you'd have a charge value and you'd know that that field goes outwards far away. So that is, and so this is electrostatics, so it's not that interesting for machines, for example, but actually it turns out that you can use electrostatics for solving a lot of magnetic problems if because you can actually model the magnets as a magnetic charge, a fictitious magnetic charge. Okay, so but we won't talk about that too much. So this is an open boundary problem. This is a closed boundary problem. It's more defined. This is actually often, well, I would argue, easier to solve. Okay, and then we can classify the boundary conditions. So we have classification of boundary conditions. So there's really three types. There's Dirac-Ley, boundary conditions. So you'll have some scalar value, for example, and that is defined as some value at say R. So for example, you might have a problem with a circle on it, and you're told that at say R naught, then it has a certain charge value, for example, at the boundary. So there is some value on a boundary that is a scalar term. Okay, so another, from magnetic fields, you could say that on and you, for example, you could say that you have subdomain 1 and a subdomain 2, and then the value of the radial magnetic flux density on 1 is equal to the value in region 2 at the boundary, or on the boundary. So that would give continuity between the surfaces. So you could this could be inside of subdomain 1 could be made of a different material to outside, but you need to have some continuity at the boundary. You need to define how the fields propagate across the boundary, and then you could set well, let me just change that to Roman numerals. I like to use Roman numerals now because then doesn't look like it's b squared. So then, the magnetic field on the surface of region of boundary 2 could be then set to 0, for example. So that's examples of Dirac-Lie boundary conditions. Then the second type of boundary condition is the Neumann. So that's a derivative term. So, for example, n could be the normal, it could be an x, or it's a change in the field term with respect to a coordinate direction, Cartesian or polar coordinate, for example. The change in the scalar potential with respect to a direction n could be equal to some value. So, for example, it will show a bit later that the derivative of, say, x is and where phi is some scalar called the magnetic scalar potential, that is related to the let's make it r, since it's got circles here. That's equal to the magnetic field intensity, and so if you set that equal to 0, then that would be the magnetic scalar potential, the scalar term, the derivative of that you're saying is equal to 0, which in a physical sense would be, say, the magnetic field in the radial. So Neumann boundaries are used a lot also because you often solve problems that are not in the you might use a magnetic scalar potential to solve a problem to simplify your solution approach. We will talk about this more, but the derivative comes about a lot on boundary conditions. And then the third type of boundary condition is just a mixed boundary condition. So you could have the derivative plus some scalar term, scalar equation, and so that could all be on some boundary gamma 1. So you'd have to define where this h is some and omega are some functions, some known function. Okay. Any questions? Okay. Okay, so now I'm going to spend the last part of the class reviewing electromagnetics a little bit, because that's the foundation of the whole class, really. There's the magnetic equations. Review of electromagnetic theory. I'm going to just go over electrostatics on one page, because I think it's important to at least summarize that. And it, but I'm going to. My favorite is magnetics. So magnetic field is not electrostatic, but electrostatics are used in power systems problems sometimes. So there's two governing equations. Gauss's law. So that's if we integrate the surface of the electric flux density, then that must equal the charge inside of it. So D is the electric flux density term. So I'm going to do my best. If I write a line above the term, that means it's a vector. So if I put a line above it, that will tell you that it's a vector term. So, you know, x, y, and z components in general. If I don't do that, then you can. It's a scalar or it's a mistake. Hopefully, I'll try not to make too many mistakes. And note that the electric flux density is related to the electric field intensity. Note D is equal to E by the permittivity. So E is the electric field intensity, and D, and where the epsilon is the dielectric permittivity of the medium. So that's equal to epsilon naught epsilon r. So this is saying that the total outwards field over a surface is equal to the net charge. So if you integrate so that this is the charge density. If you integrate the charge density over a volume, you'll get charge, which is coulombs. In the differential form, and I'll call this equation I'm going to call this equation 1 here. And in the differential form, is del dot E is equal to the charge density divided by the permittivity. And then now for static problems, we have del cross E is equal to 0. Static electric fields are irrotational. That means that they close on themselves. So what this means then is if we integrated this over a surface, then we end up with equation 4, where the electric field around a loop is equal to 0. So if you have some electric field and you integrate that all the way around a loop, that has to sum to 0, the line integral. That's used in that's commonly known as Kirchhoff's law. So then now we can from electromagnetics, we know that we can also write E in terms of a scalar potential. So E is a vector, okay? But we can calculate E, a vector, from V, a scalar, by taking the gradient of it. And so that's an important point, because, for example, if we could design a problem to solve for V, and we solve the whole problem, that might be a lot easier than trying to solve the problem for E, because V is a scalar. So if you think about that from problem formulation in terms of matrices, for example, if you only have to solve for at every point in space, if you only have to solve the value at every point in space has one known value, that's a lot easier than if every point in space has 3 components, an EX, an EY, and an EZ. So if the problem can be solved numerically using a scalar, the problem solution will be significantly reduced in terms of computational time, because you won't have to solve the 3 vectors. So understanding these relationships is really important. So we can, so that's 5. So this is, so in terms of electric potential V, we can write the electric field intensity. If we now this is 5. If we look and we can also write this as the integral. We can integrate this and get back the V, the electric potential from the electric field intensity. Now, if we look at 5 and we look at 2, right? 2 is the del operator and the dot product with respect to E. And now we've got E in terms of a scalar. So if we substitute 5 into 2, what do we get? 5 into 2 gives del squared V is equal to minus rho V over the permittivity. So this is a I can expand that out if you want. So del squared V del x squared plus del squared V del y squared plus del squared V del z squared is equal to, the right side is the charge term. So what type of equation is this called based on our classification? You remember? Is it Laplace or Poisson? So that's a Poisson equation. So we got out so this is 6, 7, 8. So this is a Poisson's equation. So again, this is a scalar term, V. So if we might be wanting to know what the electric field is somewhere, but it would be much more of a pain to have to solve directly for the electric field for the problem, because if we were to solve for the electric field, we'd need to figure out Ex, Ey, and Ez. And the way that this partial differential equation is written, we only have to solve for one unknown for the whole subdomain, V. Then, if we can figure out the solution of V everywhere, where we want it, then we can go back and then calculate E from the gradient of V. So this is actually a much better way of solving complicated problems, if you can, is to try to figure out, how many unknowns do I really have to numerically solve? Do I really have to solve Ex, Ey, and Ez everywhere? Or can I just solve in terms of one, and then at the end do a post-processing where it will calculate E from V? So that's what this allows you to do. Okay, so that's electrostatics. So next time I'll talk about magnetostatics, and then we'll go on to talk about different formulations of the magnetostatic equation. Okay.